Hello friends, welcome to our channel. In previous videos we discussed about metric space, example of metric space and induced metric space. Now in today's lecture we will discuss about semi-metric space, distance of the point to the subset, distance between the two subsets and diameter of the set. Semi-metric space. It is also known as pseudo-metric space. Let capital X be any non-empty set and D be a function from X cross X to R, that is D is a function from X cross X to R, satisfying the following properties. First property, dxy is greater than equal to 0 for every x y belongs to capital X. Second, if x is equal to y, then dxy is equal to 0. Third, dxy is equal to dyx for every x y belongs to capital X, that is symmetric property. Fourth, dxy is less than equal to dxz plus dzy for every x, y, z belongs to capital X, that is triangular inequality property. Then xd is called semi-metric space or pseudo-metric space. We see there is a minor difference between metric space and semi-metric space. In the second property we see in semi-metric space, if x is equal to y, then distance between x and y is 0. But in metric space, if distance between 2 points is 0, then points also must be equal to 0. In this case, distance between 2 points is 0, but points may be different. So, semi-metric space is also known as generalized metric space. In generalized metric space, distance between 2 points may be 0 when the points are distinct points. So, from the definition of the semi-metric space, it is clear that every metric space is a semi-metric space. But converse need not be true. That is, every semi-metric space need not be a metric space. Now we will discuss an example of semi-metric space, but it is not a metric space. Give an example of semi-metric space. Pseudo-metric space. Which is not a metric space. Let capital X be the class of all Riemann integrable functions on a closed interval 0 to 1. That is, f is a function from 0 to 1 to r. Such that dfg is equal to integral 0 to 1 modulus of f minus g x dx is equal to integral 0 to 1 modulus of fx minus gx dx. We have to check that capital X is a semi-metric space but not a metric space. So first, dfg is equal to integral 0 to 1 fx minus gx modulus dx. As we know, modulus quantity is always non-negative. Therefore, fx minus gx, its modulus is greater than equal to 0 for every f and g belongs to capital X and x belongs to interval 0 to 1. This implies integral 0 to 1 fx minus gx dx is also greater than equal to 0 for every fg belongs to capital X. This implies dfg is greater than equal to 0 for every fg belongs to capital X. Second, let f is equal to g, then fx is equal to gx for every x is belongs to interval 0 to 1. This implies fx minus gx is equal to 0 for every x. This implies fx minus gx, its modulus is equal to 0 for every x is belongs to 0 to 1. This implies integral 0 to 1 fx minus gx, its modulus is equal to integral 0 to 1 0 dx is equal to 0. This implies if f is equal to g, then dfg is equal to 0 for every fg belongs to capital X. So second property is also satisfied. Third, let dfg is equal to 0 to 1 modulus of fx minus gx dx, which is equal to 0 to 1 modulus of gx minus fx dx, because modulus of fx minus gx is always equal to modulus of gx minus fx, which is equal to d of gf. This implies dfg is equal to dgf for every fg belongs to capital X. Next, fourth, let fgh belongs to capital X. Consider f dfg is equal to integral 0 to 1 fx minus gx, its modulus dx, which is equal to integral 0 to 1 fx minus hx plus hx minus gx, its modulus dx, which is less than equal to integral 0 to 1 fx minus hx, its modulus dx, plus integral 0 to 1 hx minus gx, its modulus dx, which is equal to d fh plus d hg. This implies dfg is less than equal to dfh plus dhg. So triangular inequality is also satisfied. Hence, D satisfies all the properties of semi-metric space. This implies XD is a semi-metric space. Now we will prove that X is not a metric space. For this, we have to take example that fx is equal to 2, 0 if x x is equal to 0, if x is greater than 0 less than equal to 1, and gx is equal to 1 if x is equal to 0, 0 if x is greater than 0 less than equal to 1. Then f minus g x is equal to fx minus gx is equal to 2 minus 1 is equal to 1 if x is equal to 0, 0 minus 0 is equal to 0 if x is greater than 0 less than equal to 1. Now it is clear that f minus g is Riemann integrable on the closed interval 0 to 1 as x is equal to 0 is the only point of discontinuity. Now dfg is equal to integral 0 to 1 fx minus gx modulus dx, which is equal to integral 0 to 1 fx minus gx dx is equal to integral 0 to 1 f minus g x dx is equal to 0. Hence dfg is equal to 0, but f does not equal to g. Therefore d is not a metric on capital X. So xd is not a metric space, but it is semi-metric space. Distance between a point and subset. Let capital X D be a metric space and small x belongs to capital X. That is, X is an arbitrary point of capital X. Suppose capital A is a subset of capital X, then the distance between the point X and subset A is denoted as dxa, and defined as dxa is equal to infimum of dxa such that a is belongs to capital A. Graphically we see that the rectangular part is the metric space X with metric D. Let X is an arbitrary point of capital X and A is a subset of capital X. Then we have to find the distance between X and A, that is the minimum distance between X and A. This is the minimum, that is dxa is the greatest lower bound of distances from the point X to the subset A. For example, let D be a usual metric on the set of real numbers. That is dxy is equal to modulus of x minus y for every x y belongs to capital R, and let A is equal to 1 2 is a subset of R. Suppose x is equal to 3 by 2 belongs to R be the arbitrary point. Then dxa is equal to d 3 by 2 d 3 by 2 1 2 is equal to 0, because 3 by 2 belongs to capital A. That means the distance between the point which is lies in A with respect to the subset A is 0. Minimum distance is 0. Suppose x is equal to 5 by 2, then dxa is equal to d 5 by 2 1 2 is equal to 5 by 2 minus 2 is equal to 1 by 2. Next, diameter of subset. Let capital XD be a metric space and A is any subset of capital X, then diameter of A is denoted by delta of A and defined as delta of A is equal to supremum dxy such that xy belongs to capital A. Graphically, let the rectangular part is a metric space XD. A is a subset of capital X. Then we have to find the distance between the 2 points of A. 1 point, 1 point. This is the distance. But the maximum distance between any 2 points of A is known as diameter. That is supremum of dxy such that xy belongs to capital A is known as diameter of the subset A. If diameter of A is finite, then A must be finite. And if diameter of A is infinite, then A is also infinite subset of capital X. It is also clear that if diameter of A is finite, then A is said to be bounded set. If the distance, maximum distance between the any 2 points of the subset A is finite, then we can say the set is a bounded set. For example, let D is a usual metric on R, where R is the set of real numbers, where R is set of real numbers. Let capital A is equal to 1 and 3, then diameter of A is equal to supremum dxy such that xy belongs to capital A. This implies diameter of A is equal to modulus of 3 minus 1 is equal to 2. Suppose A is equal to 4 and 7, then diameter of A is equal to modulus of 7 minus 4 is equal to 3. Next, distance between two subsets. Let capital XD be a metric space and capital A, capital B are two subsets of capital X, then the distance between A and B is denoted by D of AB and defined as D of AB is equal to infimum of dxy such that x is belongs to A, y is belongs to B. If A and B are any two subsets such that A intersection B does not equal to phi, then distance between A and B is equal to 0. Because if A intersection B does not equal to phi, therefore there is a point which is common to A as well as in B. So the minimum distance between A and B becomes 0. It is sufficient for today. In the next video, we will discuss about examples of diameter and distance between the subsets. So keep in touch, watch our videos, subscribe our channels to more and more videos on this topic. Thanks to all. Have a nice day. Bye bye.